Another nice and clear-cut experimental evidence that atoms must have discrete energy levels came from the Frank-Hertz experiment. Gustav Ludwig Hertz was a nephew of Heinrich Rudolf Hertz, the German physicist we talked about in the lecture on the photoelectric effect. While Heinrich Rudolf Hertz, among other things, proved the existence of electromagnetic waves, Gustav Ludwig Hertz and James Franck were awarded the 1925 Nobel Prize in Physics for their discoveries of the laws governing the impact of an electron upon an atom, with the experiment we are going to describe here. This experiment consists of a gas of mercury atoms which are emitted by an electric cathode, called also an electron gun. That is something similar to the filament of a light bulb. It emits not only light but also electrons. The gas and the electron-emitting cathode are enclosed in a low-pressure bulb, where an electric field is applied between the cathode and a positively poled grating through a battery or some electric source, which builds up the electric potential. Since electrons are negatively charged particles, this difference in the electric potential field leads to their acceleration and conveys them some kinetic energy. Then, between the grating, a collecting plate on the right, and another field is applied then. When the electrons reach the grating, most of it will fly through because the meshes of the grating are kept sufficiently wide to allow for them to go through. But in this second part, in the second stage of their journey, they will experience an inverse polarized electric field, since from the grating on they will be repelled, because they will begin to feel the negatively charged collecting plate. As you should know from school, charges with the same polarity repel each others. This means that by using an amperemeter, a device which measures the electric currents, that is the flux of electrons between the grating and the collecting plate, it is possible to measure also the changes of the electrons' energy and see how their energy is affected by the atoms while flying through the gas. Franck and Hertz's idea was that while flying through the gas of atoms, several electrons must sooner or later hit one or more atoms and must be scattered elastically. They are deviated but maintain the same kinetic energy, or inelastically. This means they lose part or all their kinetic energy in the collision process. This means that there must be a measurable difference between the energy of the injected electrons and that of those which flew through the gas, which is then signaled by the measurement of the current between the grating and the collecting plate. And this energy gaps tells us something about the absorbed energy by the atoms. Therefore, if atoms absorb energy only in packets, this implies that while we slowly increase the kinetic energy of the injected electrons, we should be able to observe when and how they will be absorbed by the mercury atoms. This is indeed what happens. Look at the graph which depicts the current measured at the collecting plate. While the injected electrons' kinetic energy is increased steadily from 0 to a certain voltage, we observe that the outcoming electrons do not show to have a final kinetic energy which grows in the same manner as the increase of the electrons' input energy. What we see is that at first the relation between the input and output energy is more or less linear, and which means that the electrons are scattered through the gas elastically. They do not lose considerably their kinetic energy. But about 4 volts, the first bump appears. between 4 and 5 volts, the output energy of the electrons suddenly decreases. This signals an inelastic scattering, and that most of the energy the electrons had initially must have been suddenly absorbed by the mercury atoms. But this does not happen before a certain kinetic energy threshold of the electrons hitting the mercury atoms. Almost all the kinetic energy, about 5 to 6 volts, is lost and goes into the excitation of atoms. Then, after about 6 to 7 volts, the energy begins to increase again, meaning that the atoms absorb only a discrete amount of the electron's energy, but not more than that. All this repeats regularly at about 9 to 10 volts and 14 volts. Moreover, note that the existence of several bumps at different input energies means also that atoms must have several different energy levels. This latter fact justifies the existence of different orbits with their respective quantum numbers in Bohr's atomic model. This was another great success of experimental physics, which seemed also to validate Bohr's idea to represent the atoms in form of a model which resembles a tiny solar system. Not too many years later, also other types of phenomena confirmed energy quantization in nature. One of these was a so-called Compton scattering, due to the American physicist Arthur Holly Compton. Compton used the assumption that electromagnetic waves can also be considered as a flux of particles or photons. Then, if this is true, it is then also possible to calculate precisely the scattering process between single photons by single electrons, and also vice versa. Just like it is possible to describe the elastic collision between two billiard balls, using the simple laws of energy and momentum conservation of classical physics. Now, by using these conservation laws, Compton wrote down a nice formula which relates the wavelength lambda of an incoming high-energy gamma photon, that is, a photon with a wavelength sufficiently small to be comparable to the size of an electron, before the scattering with the electron, and the wavelength of the scattered photon, according to a scattering angle phi. The wavelength of the scattered photon must obviously be larger than the incoming one, since it loses some of its energy. For illustration purposes, the color of the incoming photon is depicted in blue, while that of the outgoing one is in red. So the higher the energy of a photon, the smaller its wavelength will be. In fact, remember that the energy of a photon is given by Planck's formula, E equal h times nu, with nu the frequency. The wavelength of an electromagnetic wave is given by lambda equal c over nu, with c the speed of light in vacuum. So the wavelength of a photon must be inversely proportional to its energy. So putting all this together with conservation laws, Compton was able to predict therefore a very strict relation, a relation between the wavelength of the incoming photon and the angle phi at which we observe it after the scattering process. Compton's formula, which relates the wavelength of the incoming and scattered photon, is this one that you can see, lambda prime minus lambda, where lambda prime is a scattered photon, the wavelength of the scattered photon, lambda of the incoming one. This is equal h over MEc, where Me is the mass of the scattering particle, in this case the electron's rest mass, and c obviously, as usual, the speed of light in vacuum, and times a term 1 minus the cosine function phi, the scattering angle phi. Notice that if phi is 0, we have no difference, which means no scattering occurred. While for phi equal 180 degrees, that is for backscattering, the wavelength shift is twice as much. The possibility to know precisely the relation between the input and output energy of the particles and their respective scattering angle was finally verified experimentally, and it turned out to follow precisely the predictions of Compton's formula. Compton scattering is also an atomic scattering process. A gamma photon can be scattered by the electrons in the atomic shell of atoms. This is not the same ionizing process we saw in a previous lecture. Here, ionization does not occur. In the picture you can see an example which makes it also clear how only a part of the energy of the photon is transferred to the electron, and therefore to the atom. A high energy photon that is scattered by several atoms will lose collision after collision its energy, and from a small wavelength, high frequency, photon will become a large wavelength, which means low frequency photon. By the way, it may also be interesting to point out that this is an effect that plays also an important role in the center of the Sun. In the Sun's core, which has temperature of about 60 millions of degrees, there is a huge amount of gamma radiation. It takes, however, several millions of years of scattering of many scattering processes until the photon produced at the core inside the Sun reaches the surface, where it will have lost most of its energy, and then the photons we observe nowadays coming from the Sun's surface, we are able to see them, which means that the photons that we see today have been in reality being created in the center of the Sun many millions of years ago. What makes Compton scattering also so important and interesting is that all this seems to suggest that we can equally well consider electromagnetic waves no longer as waves at all, but think of light particles, of photons, like tiny billiard balls. If we would stick to the idea that light is made of waves, we should observe a very different kind of scattering. A scattering of concentric waves by the electron. Compton scattering instead indicates that the application of the conservation laws of classical physics, which determine the scattering between classical particles, holds also with photons if we think of them as particles. There is therefore no longer any reason to reject a particle picture in quantum mechanics instead of the wave picture. Another effect which is worth mentioning is the pair creation effect, discovered in 1933 by the British physicist Patrick Blanket. This phenomenon clearly showed that we must conceive light not only as made of photons, but also that they can transform in other material particles like electrons. Pair creation or annihilation, which is the opposite process where particles with a mass are converted into photons, is a striking example of Einstein's energy-mass equivalence, which is described by Einstein's famous formula E equal mc square, where m is the rest mass of the particle, and this energy is also called the rest energy. The energy-mass equivalence tells us that every particle, atom, or any material object with a mass m contains an energy in potential form, which is given by Einstein's formula. The fact that there is the speed of light squared in it makes the amount of energy that matter contains extremely huge. A gram of matter, if converted in kinetic energy, would produce an explosive effect like the bomb of Hiroshima. Pair creation is precisely a physical phenomenon whereby photons could be converted into material particles. One of the material outgoing particles will be a negatively charged electron, while the other is a positively charged, so-called anti-electron. Anti-electrons are just those particles which, if they come into contact with ordinary matter, annihilate to produce photons according again to Einstein's mass energy equivalence. The annihilation process occurs in the opposite direction, therefore. Massive particles, typically an electron and anti-electron, are converted into energy, or into photons more precisely. Antimatter in general is made of the same particles with the same mass, that is, of electrons, protons, neutrons, etc., but with the opposite electric charge. Fortunately, for some reason still not entirely clear, the universe we live in is made only of, or almost only of, one type of particles, the particles, not the antiparticles. Otherwise, we would have already would evaporate away in a foamy universe where free particles annihilate and create itself continuously. Pair creation can happen in alternative to Compton scattering. Instead of the photon and electron being scattered, what occurs in this case is an absorption of the photon and an immediate re-emission in form of completely different particles. This process, however, can only happen if the energy of the incoming photon is sufficiently large to produce the two electrons according to Einstein's formula. If the photon's energy is lower than twice the rest energy of two electrons, the process cannot occur. So we have listed so far several phenomena which indicate how energy is absorbed and emitted in a quantized manner, and therefore leads also to the corpuscular nature of light, to the interpretation of the corpuscular nature of light. We have seen the blackbody radiation, the photoelectric effect, the Frank-Hertz experiment, the Compton effect, as also pair creation and annihilation. These are a sufficient number of observational evidence, experimental evidence, that justify also the name of quantum physics, quantum mechanics, or quantum theory. However, one could also perform several other experiments which would show that light behaves in the opposite way, as a wave, in fact, as we shall see in the next chapters, in the next lectures. The question at this point is, if light is made of particles, how can it be that, for example, we observe interference phenomenon in light? All the physics previous to quantum theory was based on the assumption that light is a wave. Now quantum theory seems to put things all upside down. Which of the 2 points of view are correct? And this is precisely what we are going now to look into more detail in the next lectures.